Welcome back, fellow explorers. Last time we took a remarkable journey together, didn't we? We discovered that intelligence isn't some rare, mystical quality possessed only by genius in ivory towers. Instead, we found it everywhere. In the clever crow dropping stones into a pitcher, in a child's brain rewiring itself as those little fingers learn to tie shoelaces, in your own mind as you recognize a friend's face among thousands, or figure out how to navigate a blocked road. We saw that intelligence is really about how we navigate our world, how we learn from experience, reason about what we observe, solve problems creatively, and adapt to whatever life throws our way. It's the common thread connecting you, me, that crow, your pet, and even the artificial minds we are beginning to create. But here is what's fascinating about human curiosity. Once we notice something remarkable in nature, we can't help but want to understand it more deeply. And for thousands of years, brilliant minds have asking the same questions we explored together. What exactly is intelligence? How does it work? Can we understand it well enough to recreate it? The beautiful thing is that different fields of study have developed their own unique ways of approaching these questions, like scientists looking at the same mountain through different telescopes, each revealing detail the others might miss. Today, we are going to look through three different lenses at the same phenomenon we have been exploring. Think of it this way. If intelligence is like a diamond, then each lens shows us different facets of the same precious stone. None of them tells the complete story alone, but together they're painting a picture of intelligence that's richer and more fascinating than any single perspective could reveal. We'll peer through the psychologist lens and discover how the human mind might actually contain not one intelligence, but many different kinds working together in harmony. We'll look through the neuroscientist lens and see how thoughts and learning literally reshape the physical structure of our brains. And we'll examine intelligence through the computer scientist lens and explore whether the machines can truly think and what that even means. Each lens will show you something different, something surprising, and something that connects back to that everyday intelligence you experience every moment in every moment of your life. By the end of our journey today, you'll see that crow, that child, and your own remarkable mind in an entirely new light. Are you ready to see intelligence from three fascinating perspectives? Let's begin with the first lens. The one that revealed intelligence might be far more diverse and wonderful than we ever imagined. Let's begin with a story that changed how we think about intelligence forever. Picture this. It's the 1970s, and a young psychologist named Howard Gardner is working with people who have suffered brain injuries. Day after day, he observes something that puzzles him deeply. Here is what Gardner noticed. A patient might lose the ability to speak or write after damage to one part of their brain, uh, but, but their mathematical abilities remained completely intact. They could still solve complex equations, understand numerical relationships, reason through logical problems, yet they couldn't form a simple sentence. Another patient might lose their mathematical reasoning entirely, but could still paint beautiful pictures, navigate through complex spaces, or compose moving pieces of music. This was profoundly mysterious. If intelligence was truly one unified ability, one general smartness that powered all our thinking, then shouldn't brain damage affect all intellectual abilities equally? It was like discovering that damaging one room in a house somehow left all the other rooms completely untouched. Gardner began to suspect something revolutionary. Maybe intelligence wasn't one thing at all. Maybe the human mind contained not one intelligence, but multiple intelligences, each with its own unique characteristic, each operating somewhat independently of the others. Think about the people in your own life, and you will start to see what Gardner was discovering. You probably know someone who has what we might call musical intelligence. This is that friend who can listen to any song once and immediately play it back onto the piano, or who can hear a complex piece of music and instantly tell you it's in the key of D minor. They seem to have an intuitive understanding of rhythm, melody, harmony. They think in musical patterns the way others think in words or numbers. When they hear music, something different happens in their brain than what happens in yours or mine. Or consider spatial intelligence. You know that person who never ever gets lost. They can drive to a place once and somehow their brain creates a perfect mental map. They can look at a complex piece of furniture from IKEA and immediately visualize how all those confusing pieces fit together. They can rotate three-dimensional objects in their mind like they are holding them in their hands. While you might struggle to parallel park, they see spatial relationships as clearly as you see colors. Then there is interpersonal intelligence, perhaps the most mysterious and valuable of all. This is that person who always seems to know exactly the right thing to say. They can walk into a room full of strangers and immediately sense the emotional undercurrents, the unspoken tensions, the hidden dynamics. They understand not just what people are saying, but what they mean, what they need, how they are feeling. They are like emotional detectives reading clues that the rest of us miss entirely. Now, here is what's truly fascinating. These different forms of intelligence can exist in the same person at wildly different levels. Your musical gifted friend might get uh, hopelessly lost driving to the concert hall. The spatial genius might struggle to read the emotional atmosphere of a room. The interpersonally intelligent person might be completely tone deaf. This observational led Gardner to a radical conclusion. Intelligence isn't like height or weight, a single measure that applies to everything. Instead, Intelligence is more like a toolkit with different tools for different jobs. Just as a master carpenter might be brilliant with a saw, but clumsy with a paintbrush, a human mind might excel in one type of intelligence while being perfectly ordinary in another. But this raises a profound question that psychologists are still debating today. Is intelligence really one fundamental ability that shows up in different ways, or is it truly multiple separate abilities that just happen to coexist in the same brain? Some researchers argue for what they call general intelligence, an underlying mental energy that powers all intellectual tasks. They point out that people who excel in one area often excel in others too. If you are good at math, you are likely also good at reading comprehension, logical reasoning, and spatial tasks. Others, following Gardner's lead, insist that the evidence clearly shows distinct, independent intelligences. They argue that traditional IQ tests measure only a narrow slice of human intellectual capability, mainly logical and linguistic intelligence, while ignoring the full spectrum of human mental gifts. The truth, as often happens in science, might be more nuanced than either extreme position suggests. Perhaps we have both some general intellectual capacity that influences all our thinking, plus specialized intelligences that allow us to excel in particular domains. What's beautiful about this debate is that it's changed how we think about human potential. Instead of asking, how smart are you? We have learned to ask, how are you smart? Instead of seeing intelligence as a fixed quantity, we have begun to see it as a diverse landscape of different mental abilities, each valuable in its own way. And this shift in understanding human intelligence has profound implications for how we think about artificial intelligence. If human intelligence is really multiple intelligences working together, then perhaps the path to creating truly intelligent machines isn't to build one super smart system, but to create multiple specialized intelligences that can collaborate and complement each other. The psychologists' lens has shown us that intelligence is far richer, far more diverse, and far more interesting than we ever imagined. But to understand how these different intelligences actually work, we need to look deeper into the brain itself. Now, let's shift our perspective and look at intelligence through the neuroscientist lens. If psychologists showed us that intelligence might be multiple abilities working together, neuroscientists have revealed something equally amazing. We can actually see intelligence at work by looking directly into the living brain. But to understand what neuroscientists have discovered, let me give you a way to think about your brain that will change how you see your own mind forever. Imagine your brain as a vast, bustling city. Not just any city, but the most complex city ever built, with about 86 billion inhabitants. These inhabitants are your neurons, your brain cells, and just like people in a city, they need to communicate with each other constantly. In this neural city, different neighborhoods specialize in different activities. There is the visual district at the back of your head, constantly processing everything you see. There's the language quieter, usually on the left side, where words are understood and formed. There is the motor district, where movements is planned and coordinated. And there is the memory district, where your experiences are stored and retrieved. But here is what makes this city truly remarkable. The roads connecting these neighborhoods, what neuroscientists call neural pathways, are constantly being built, strengthened, and sometimes abandoned based on how often they are used. It's as if the city redesigned its entire transportation systems every single day based on where people actually need to go. When you practice something, anything, you are literally sending more traffic along certain neural pathways. And just like a city that builds wider highways where traffic is heaviest, your brain strengthens these pathways, making them faster and more efficient. This is neuroplasticity, the brain's ability to physically reshape itself based on experience. Now, you might think this sounds like a nice metaphor, but let me tell you about one of the most stunning pieces of the evidence that this is exactly what happens in real brains with real people. In London, there is a group of people who undergo one of the most demanding tests of spatial memory in the world. To become a licensed black cab driver in London, you must pass something called the knowledge. This means memorizing by heart every single street, every landmark, every possible route through the maze-like network of 25,000 cities that make up London. Most people spend 3 to 4 years studying for this test, many never pass. A brilliant neuroscientist named Eleanor McGuire wondered, what does all this intensive spatial learning do to the brain? So she took brain scans of London taxi drivers and compared them to the brains of people who drove around London regularly but hadn't undergone this intensive training. What she found was absolutely extraordinary. The taxi drivers had physically larger hippocampi, the brain's region responsible for spatial memory and navigation, not just slightly larger, significantly larger. It was as if all that practice navigating London streets had literally grown that part of their brain. But here is the truly remarkable part. The longer someone had been a taxi driver, the larger their hippocampus. This wasn't something they were born with. This was their brain physically changing, growing, adapting in response to the demands placed on it. Think about what this means for a moment. Every time you practice piano, your brain physically changes. Every time you learn a new language, new neural pathways form and strengthen. Every time you solve a math problem, you are not just using brain, you are reshaping it. Your brain is like a muscle, but far more sophisticated than any muscle. It doesn't just get stronger with use, It literally rewires itself to become better at whatever you are practicing. This is happening in your brain right now as you listen to this word. Neural connections are firing, pathways are strengthening, and your understanding of intelligence is quite literally becoming wired into the physical structure of your mind. But neuroplasticity reveals something even more profound about intelligence. Remember how we thought about different types of intelligence in the psychologist's lens? Well, neuroscientists can actually see these different intelligences lightening up in different brain regions. When someone is processing music, their auditory cortex becomes highly active. When they are solving spatial problems, their parietal cortex takes the lead. When they are reading social cues, their prefrontal cortex and temporal regions work together in complex ways. Your brain is constantly rewiring itself based on what you do, what you practice, what you experience. This means that intelligence isn't fixed. It's not something you are simply born with and stuck with forever. Intelligence is dynamic, growing, changing throughout your entire life. This has profound implications for how we think about learning, about human potential, about artificial intelligence. If biological intelligence emerges from patterns of connections between neurons, if it can grow and change throughout experience, then perhaps we can understand these principles well enough to create similar patterns of learning and adaptation in artificial systems. The neuroscientist lens has shown us that intelligence isn't just abstract mental process. It's physical, measurable, and constantly evolving. But there is one more lens we need to explore, one that asks perhaps the most intriguing question of all. If we understand intelligence well enough, can we recreate it in machines? Now let's turn to our third and perhaps most intriguing lens, the computer scientist perspective. And to understand this lens, we need to travel back to 1950 to a brilliant mathematician named Alan Turing, who asked a question that still echoes through the halls of science today: can machines think? Turing wasn't asking this question in some abstract philosophical way. He was deeply practical about it. He said, in a sense, look, instead of trying to define what thinking really is, which philosophers have been arguing about for centuries, let's ask a simpler question. Can a machine have a conversation so convincing that a human being can't tell they're talking to a machine? This became known as the Turing test, and it shifted the entire conversation about machine intelligence from what is thinking to what does intelligence behavior look like. It was a stroke of genius, really, because it gave us something we could actually test and measure. But here is what is fascinating. While we are still working toward machines that can pass Turing full test, computer scientists have discovered that machines can already display remarkable forms of intelligence in specific narrow domains. And the most amazing part, you interact with these intelligent machines every single day without even thinking about it. Let me show you what I mean. Think about your email inbox. Every day, dozens, maybe hundreds of emails arrive, and somehow, miraculously, the spam messages get filtered out automatically. But how does your computer know what is spam and what isn't? It's not like there is a programmer somewhere writing rules that say if an email mentions a Nigerian princess, it's spam. Instead, your spam filter is actually learning. It's observing patterns in millions of emails, noticing that certain combinations of words, certain sending patterns, certain characteristics tend to appear in messages that human marks as spam. Over time, it builds a mathematical model of what spam looks like. And here is the remarkable part. It gets better with experience. The more spam it sees, the better it becomes at recognizing new spam that it's never encountered before. This is machine learning in action. Your computer is demonstrating a form of intelligence, the ability to learn from experience and apply that learning to new situations. Or consider something even more personal. How does Netflix seem to know exactly what movie you'll want to watch on a Friday night? You might think it's magic, but it's actually a sophisticated form of pattern recognition. Netflix is constantly learning about your preferences. It notices that you watch 3 romantic comedies in a row, that you always skip action movies with certain actors, that you tend to watch documentaries on weekdays but comedies on weekends. But it doesn't stop with just your viewing history. It's simultaneously learning from millions of other viewers, finding people whose tastes are similar to yours and using their preferences to predict what you might enjoy. It's like having a friend who knows your taste perfectly, but this friend also knows the preferences of millions of other people and can spot patterns that no human mind could ever track. This is recommendation intelligence, the ability to find patterns in vast amounts of data and use those patterns to predict what you might want or need. And then there is perhaps the most conversational form of artificial intelligence you encounter regularly: voice assistants. When you say, "Hi Siri, what's the weather going on to be like tomorrow?" something remarkable happens in that brief moment. The device has to convert your speech into text, figure out that you're asking about weather, determine what tomorrow means in the context of today's date, looks up weather information for your specific location, and then convert that information back into natural surrounding speech. But here's what makes this truly intelligent behavior. These systems understand context. If you follow up by asking, "What about the weekend?" the assistant knows you are still talking about weather, even though you didn't say the word weather. It's maintaining a conversational context, something that requires a sophisticated understanding of how human communication works. Each of these examples represents a different flavor of machine intelligence. Pattern recognition, like spam filter, predictive modeling, like Netflix, natural language understanding, like voice assistants. What's fascinating is that these different types of intelligence map remarkably well onto the different type of human intelligence we explored through the psychologist's lens. But here's the key insight that computer scientists have discovered. Computers are getting remarkably good at specific types of intelligence, often surpassing human performance in narrow domains. A computer can beat the world chess champion, recognize faces more accurately than humans, or translate languages with a stunning fluency. But these same systems that excel in one area often fail completely in others. This tells us something profound about intelligence itself. Perhaps intelligence isn't one monolithic ability, but rather a collection of specialized capabilities that can be developed independently. A chess-playing computer doesn't know how to have a conversation. A translation system can't recognize faces. Each system excels in its specialized domain but lacks the flexible, general intelligence that humans take for granted. This is leading computer scientists to a fascinating realization. Creating artificial general intelligence, the kind of flexible, adaptable intelligence that humans possesses, might require not building one super intelligent system, but rather building many specialized intelligence systems that can work together, communicate with each other, and complement each other's strengths. The computer scientist lens has shown us that machine intelligence is not only possible, it's already here, working alongside us every day. But it's also revealed just how complex and multifaceted true intelligence really is. The very process of trying to recreate intelligence in machines has taught us things about intelligence that we never could have learned any other way. And this brings us to a beautiful realization. These three lenses, the psychologists, the neuroscientists, and the computer scientists, aren't competing waves of intelligence. They are complementary perspectives on the same magnificent phenomenon. Now, here is something beautiful that I want you to notice. As we have looked through these three different lenses, the psychologists, the neuroscientists, and the computer scientists, you might have noticed that they are not telling three different stories about intelligence. They are telling the same story from three different vantage points, each revealing details that the others might miss. Think of it like this. Imagine you are trying to understand what a magnificent cathedral looks like, but you can only observe it from one position at a time. If you stand in front, you see the grand facade, the soaring towers, the intricate stonework. If you walk around to the side, you notice the flying buttresses, the way structure supports itself. If you go inside, you experience the vast interior space, the play of light through stained glass windows. Each viewpoint shows you something true about the cathedral, but none of them alone captures its full majesty. That's exactly what's happening with our understanding of intelligence. The psychologist's lens revealed that intelligence comes in multiple forms, that musical ability and spatial reasoning and social understanding might be distinct capabilities. The neuroscientist lens showed us that these different forms of intelligence actually correspond to different brain regions working together, and that our brains physically reshape themselves based on what we practice. The computer scientist lens demonstrated that we can recreate specific types of intelligence in machines, but also revealed just how specialized and narrow artificial intelligence currently is compared to the flexible, general intelligence that humans possess. But when you step back and look at all three perspectives together, a remarkable picture emerges. Intelligence appears to be both unified and multiple, both biological and computational, both fixed in some ways and incredibly plastic in others. It's like discovering that light is both a wave and a particle, that two seemingly contradictory descriptions can be both be true depending on how you look at the phenomenon. The psychologist says intelligence is multiple abilities working in concert. The neuroscientist says these abilities emerge from neural networks that strengthen with use. The computer scientist says we can recreate aspects of these abilities in artificial systems, but each system excels in narrow domains. Put it all together, and you get a picture of intelligence as a collection of specialized but interconnected capabilities that can learn, adapt, and grow through experience. This convergence isn't coincidental. It's pointing us towards something fundamental about the nature of intelligence itself. Whether we are talking about a human brain's learning to navigate London street, or a computer system learning to recognize spam, or a child's mind grasping the pattern of language, we are seeing the same understanding principle at work: pattern recognition, learning from experience, adaptation to new situations, and the ability to apply knowledge to solve problems. Each lens has enriched our understanding, and together they are painting a picture of intelligence that's far more nuanced and fascinating than any single perspective could reveal. The psychologist's insight about multiple intelligences help computer scientists design better AI systems. The neuroscientist discovers about the brain plasticity inform psychological theories about learning. The computer scientists' work on machine learning sheds new light on how biological intelligence might actually work. But this convergence of understanding raises a new and intriguing question. If intelligence is so complex, so multifaceted, if it expresses itself in so many different ways across different minds and even different types of minds, then how do we measure it? How do we quantify something that seems to resist simple categorization? The question has puzzled scientists for over a century, and the attempt to answer it have led to some of the most contentious debates in all of psychology and cognitive science. From the first IQ test to modern assessment of artificial intelligence, the challenge of measurement has forced us to confront fundamental questions about what intelligence really is and what it means to be intelligent. Next time, We'll explore this fascinating challenge together. We'll discover how scientists have tried to measure intelligence, what those measurements tell us, and what they miss, and why the quest to quantify intelligence has revealed as much about our own assumption and biases as it has about intelligence itself. We'll see how the question, how do we measure intelligence, leads inevitably to even deeper questions about fairness, human potential, and what it really means to understand the mind. The journey of understanding intelligence is far from over. In fact, we are just getting started.